Hello, I'm Connor Sanders. I'm a senior computer engineering major at Tennessee Tech, and today I will be talking about smart pointers in C++ for Capstone 2. For a little bit of background, um, pointers in C++ are objects that store memory addresses. Um, Pointers can store the address of almost anything that you would need to store in C++, whether that is a variable, an array, a function, user-defined data types, and even other pointers. Pointers allow programmers to access and manipulate any data that can be stored in a computer's memory. Here I've written a small program to show how pointers work. Um, I have made a pointer and allocated the memory, and then set the value at that memory to 25. I then used cout statements to show the memory address and the value. So if you see at the bottom, we can see that it prints out the memory address of the pointer and the value that is stored at that memory address. I'm sure most of us have used pointers at some point, maybe in an introductory C++ class. And I'm sure that we remember a few problems that we might have had while using pointers. Um, to start, when a program allocates memory for a pointer and doesn't free this memory when it's finished, whatever value is placed at that memory address gets stuck there. This is called a memory leak, and it can lead to some pretty serious issues with the machine that your program runs on. Secondly, dangling pointers can also be a problem. Dangling pointers are pointers that point to memory that's already been freed. So if you are using a pointer and then you delete it to free the memory, somewhere else in the program, you can call this pointer again, and it still holds the same memory address, but there's no value associated with it, and it can lead to inaccurate data within your program. Lastly, we can run into a problem called wild pointers. Um, Wild pointers are pointers that get declared but never initialized. So they point to some arbitrary memory location, and we can't really be sure where this memory location is at or what we might overwrite at this memory location. The real problems that we run into with pointers are that they rely on the programmer to manually allocate and free the memory. And as we might know, this doesn't always happen as it should. In this example, I've created a memory leak. So I have made a pointer and initialized the value, but I never deleted it. So this means that even after the program is finished running, the value 25 is going to stay at whatever memory location this pointer points to. Here I've created a dangling pointer. This pointer is created, the memory is allocated, we assign a value to the memory address, and we even remember to delete the pointer when we're done to free up the memory, as we should. The problem here is that we can still use this memory address somewhere else in our program. So if you look at the results, you can see that at the memory address, the value is 25. And then after I have freed the memory, We have the same memory address, but the value isn't accurate. Um, Here I've declared a pointer, but haven't allocated any memory for it. This means that some arbitrary memory address is going to be used. And like I previously stated, the problem here is that we can't be sure where the memory address is or what is stored at the memory address. So smart, oh, so smart pointers aim to solve all of these problems. We can use smart pointers in place of regular pointers. They can be used in all of the same spots that we would usually use normal pointers. Um, Smart pointers automate memory management for us so that the programmer doesn't have an option to screw it up on their own. There are four types of smart pointers, but today I'm only going to be talking about two of them. A unique pointer only exists inside of a single scope. Um, so if we use a unique pointer in a function, as soon as the function ends, um, as soon as the program gets through the function, this pointer will be deleted. Um, and there can only be one reference to this pointer, which means that the unique pointer only has one ownership of the memory address. So we can't have two pointers pointing to the same address when we use unique pointers. This avoids issues where we might have a pointer that points to an address that has already been freed. And then shared pointers are a little bit more complicated on the back end, but they're still pretty easy to implement. They make use of reference counting to track how many pointers use the same memory address. This means that multiple pointers can point to the same memory address without an issue. Um, Shared pointers are helpful because the memory will not be freed until the reference count is 0, which means that no pointer needs access to that memory address anymore. Uh, so smart pointers automatically allocate and free memory to ensure that the programmer doesn't forget to. On the left, I've created a class to represent a rectangle. I've then created a unique pointer and printed the area. You can't see it, but after the program exits the main function, the memory is freed. And then over on the right, I have done the same thing where I made the rectangle class and then I made a unique pointer and printed the area. But I have tried to make a second unique pointer that points to the same memory address as the first one, and it's thrown an error. So this is going to avoid any problems that we might have with dangling pointers because we know that there's only one pointer that has access to that memory address. And then we're going to avoid other issues because we know that the memory is automatically freed once we get out of the main function. In this example, I've created the same rectangle class, um, but instead of a unique pointer, I've created a shared pointer. Um, and then I created a second shared pointer that points to the same memory address as the first. Um, and I have also printed out the reference counter. So here we can see that both pointers hold the same value for area. And we can see that the reference counter shows 2. So there are 2 pointers that use the same memory location. So after this program is finished running, the reference count will go down to 0 and then the memory will be freed. Um, so this means that we'll never free the memory unless no pointer is pointing to that address anymore, which avoids the dangling pointers issue. And like the unique pointers, we um, automatically free the memory when we're finished. These are the sources that I used. I appreciate your time and thank you for listening.